Okay, so welcome back for part two of this section 8.2. Sorry, I got lost where I was. We're doing hypothesis testing on a population proportion. Claims, hypotheses, data, run the test, get an answer, and then interpret that answer in terms of the test. Okay, let's get started. An airline claims that the no-show rate for passengers is less than 5%. Claims less than 5%. So there's my claim. I have a population proportion that I have a claim of it being less than 5%, less than 0.05. That's going to help me set up my hypotheses. Because the claim doesn't have anything about equal in it, that means that the claim is going to be the alternate hypothesis that P is less than 0.05. And that our null will be that P is equal to 0.05. Okay. Now I need to gather some data. There's data in the problem. I can find it. Let's see. In a sample of 420, so N is 420, 19 were no-shows. So that means we saw success 19 times. And we also have an alpha level of 0.01. Now, I just realized something. In the last two examples I did, I neglected to test to make sure we could do this. And I'm sorry about that, because when I'm doing hypothesis testing, I'm supposed to be checking this, right? That my sample is big enough. My problem is both times the samples were large enough where I just kind of overlooked that, and I'm sorry. I really should have been looking at that, right? It is a necessary requirement that we check both success and failure to make sure it's bigger than 5. Here we knew success was bigger than 5 because X was 41, and if X was 41, then was that 59 failures? Again, bigger than 5. Same thing here. With this huge one, I just neglected. So I'm sorry about that. I want to point it out and check it here, right? This is our number of successes, and by definition, X is equal to our P hat times N. So that means that if this is our number of successes at 19, it's way bigger than 5. If there are 420 people and 19 of them are successes, 401 are failures, which is the other thing we're supposed to test, and definitely way bigger than 5. Right? So we're good there. Right? All right. I've got this all set up. I'm going to run the test now. Stat test 1 prop z test. My P sub 0 is 0.05. It is from the null hypothesis. My X is 19. My N is 420. And I'm doing a left tail test again. Right? I'm going to calculate it out, and then I get a p-value of, let's see, what's my p-value? 0.32. Now, from the problem, we were told that alpha is 0.01. My p-value is greater than alpha, so I will fail to reject. Okay? Remember, the claim was the alternate here. So I'm going to go back to my table. Okay. The data said fail to reject. The claim was the alternate. I'm here. So then we would say there is not enough evidence to support the claim. So then to answer the question, we would say there is not enough evidence to support the claim of a less than 5% no-show rate. Okay. Now, in the original setup, when I was talking about what we're doing in this session. I said we were going to do this with p-values, but I would also show you how to do this. What is this thing doing up here? To do this using cut scores and critical values. And I want to just talk about that with this problem right here. Right? All right, so here's how the critical value cutoff business would work with this. Our alpha level is 0.01. We are running a left tail test. That means there is going to be some number right here where everything to the left of it is going to be reject. Everything to the right of it is going to be fail to reject. Right. This tail is going to have an area or a size of 0.01. That means that this over here, all of that is going to be 99, right? I need to know this number right here. And because a z-test is what we're essentially running, what I need is I need a critical value, that's what we call that, for a left tail of 0.01. And the way that I'm going to find that, is I'm going to go back to something we did before. Remember when we did distributions, inverse normals? And I want to find an area of 0.01. And so that would give me that this cut here is negative 2.32 as a z-score, right? So now if I were to take this data and turn that data into a z-score, and I hope you kind of remember how to do that from our binomial approximations, right? So when I convert that to a z-score, it's going to fall somewhere on that horizontal axis. And if it's any number left of negative 2.32, then we'll reject the null hypothesis. And if it's any number to the right, we will fail to reject. So if I go back and I run that test again, numbers aren't changing. Oops, I still want a left tail. Do you see how the z-score is negative 0.44? Which means the data ended up about here at negative 0.44, just left of middle, which clearly puts us in the fail to reject region. Now, back in the day, this is how hypothesis testing was done. Every single time you'd figure out that critical value, and then you'd find your standardized test statistic, and then you'd figure out whether your standardized test statistic fell into the rejection region, what we have shaded yellow here, or in the fail to reject region. Right? That is just the other way or another way of solving these problems. It's not a better way, it's not a worse way, it's just a different way. It is falling out of favor in the sense of p-value is just faster. You have an alpha, you have a p-value, compare those two numbers and you're done. And since technology is doing the work for us, p-value is faster. Before tech, when we had to do everything by hand and look everything up in tables, rejection regions made sense. We just don't do that anymore. There's no reason to. There's no logic to doing things the hard way when there is an easy way. So we use the simpler, the faster p-value method. Okay? All right. Moving right along. We've got, what, 2 more examples and then we're done with this section. The engineering school at a major university claims that 20% of its graduates are women. All right, I read a claim. They have a claim that it's 20%. Right? As a statement about a population proportion, that is a statement of equality that P is exactly 20%. Now, since that claim contains equal to, that makes the claim the null hypothesis. Our alternate would then be that it's not equal to 20%. I need some data so I can run a test. So I'm going to go through and see what I can find in a graduating class, in a class of 210. So there's my data sample size. 58 were women. Okay, so there's my success rate, or my number of successes, not really a rate, but a straight up number of successes, 58. And I want to use a significance level of 0.05 to run this test. Since the claim is about a population proportion, I'm going to run a 1 prop z test. It's going to ask me per a p sub 0. That is the equality statement from the null hypothesis, so that's 0.20. It's going to ask me for an x, that's our 58. It's going to ask me for an n, that's our 210. It's going to ask me, what kind of test is this? And since it's a not equal to there, that makes it a not equal to there, or a two-tailed test. And then I'm going to calculate it. And I get that my p-value is 0.006. That means that p is way less than alpha. And when p is less than alpha, we reject the null. But the claim was the null. All right, let's go see what that means. Back to my table. Math says reject the null. The claim was the null, which means we're here. And we would say that there is sufficient evidence to reject the claim. So I'm going to come back down here, and I'm going to say, okay, what does this mean? It means that there is enough or sufficient, or however we want to say that, evidence to reject the claim that 20% are women. Okay. All right, so there it is. I got a standardized test statistic of 2.76 here. Now, if you're thinking in terms of normal distributions, right, that's like way over here. Because the middle is 0, so a 2 would be way over to the right. So that's what's happening here. We got a value that is way to the right. It must have fallen into that right-hand tail rejection region for this problem. All right, our last example. A coin is tossed 1,000 times and 507 heads appear. At a significance level of 0.05, test the claim that this is not a biased coin. Okay, so my claim is it's not biased. Okay, so what does that mean? Well, if my claim is the coin isn't bad, isn't biased, then essentially I'm saying the coin is good. And if the coin is good, what should be the proportion of heads? Well, it should be about half. I'm not even should be about half. It should be half, 50%. So if the claim is a statement of equality, that means it's the null. The alternate then is the coin is biased. Right? Wow. Okay. Does a two-tailed test make sense here? I mean, I guess it would if I'm thinking about it like this, right? It should be here at 50%. And if I got a really low percentage of heads, I would think something was wrong with the coin. Or if I got a really high percentage of heads, I would think that something was wrong with the coin. I only think the coin isn't bad, isn't biased, if I get something in the middle close to 50%. Okay, I feel good about this test now. Two-tailed test makes sense. Data, tossed 1,000 times. So we ran the experiment 1,000 times. X is 570. That is probably one of the worst of thousands I've ever written. Let's fix that. All right. N times P is X, 570 successes. That's good. If there's 570 successes, then N times Q would give me 430 failures. Both of those are way bigger than 5, so I'm not really worried about it. All right. My sample size is sufficiently large enough to run the hypothesis test, and I got a significance level of 0.05. I got everything I need. Back to stats, over to tests, down to one prop z-test, because this is a one proportion test with a z-test is doing the math. My p sub 0 is 0.5 from the null hypothesis. My x is 570. My n is 1,000. And I'm running a not equal to two-tailed test. Hey, what does draw mean down here? If I were to draw this, well, if I were to draw this, essentially what it's doing, it's going to draw the normal distribution. It's going to show me the standardized test statistic there at 4.42 and attempt to plot that. The problem is, the challenge is, whoever programmed this assumes that you only kind of want to see 3 above and 3 below the middle here. And the fact that our z-score is 4.42 means it's way over to the right of the screen. This is the p-value there. It's calling p0. But if I go back and run this test again and don't do that silly graph, and I just tell it to calculate the value for me, you'll see that p is technically not 0. Our p-value is 0.1234596. That 9.95 e negative 6 is standard deviation, or is scientific notation. Scientific notation with a negative exponent, move the decimal place left that number of places, in this case 6 decimal places, which is why we have 5 leading zeros here. Now, this is ridiculously small for a p-value, so our p-value is way less than alpha, and when p is way less than alpha, we reject the null hypothesis. The claim was the null hypothesis. So I'm going to go back to my little chart, and what does my chart tell me to do when the math says reject the null and the claim is the null? Oh, it's the same as the last time. There's sufficient evidence to reject the claim. So I can come down here and I can say there is enough evidence to reject the claim that the coin is not biased. All right, so what does that mean? Is this a fair coin? No, the evidence rejects that claim. The evidence says this coin is not fair. Now, I know what you're thinking. Could that have happened by random and it actually is a fair coin? Yes, it could have happened by random. And there is tenths, hundreds, thousands, 10,000s, 100,000s, 96 10 millionths of a chance that it could have happened by random. This is so small that we're basically saying, yeah, no, it is highly, highly, highly unlikely that this could have happened by chance. There's a lot of evidence here, sufficient evidence, enough evidence to argue this coin is biased. This brings us to the end of section 8.2. I hope it worked. Please, if you have any questions, if you want further clarification, please reach out. I know this stuff can be somewhat challenging. Have a great day.